Okay, so everyone with me, we're working on this table. We want to do a one-way Anova hypothesis test. So if you want to follow along, this is how I'm doing it. Remember on this one, for the example, we're going to add each of these observations, 7 squared plus 8 squared, which came from here, 7 squared plus 8 squared plus 15 squared, all the way down to 20 squared, minus 383, remember where that came from? So what I'm going to do is I'm going to go B3 squared right there, that first sample in the control group squared, plus C3 squared, plus D3 squared, and I'm just going to add all of these. So I'm going to do a little, there is a little shortcut if you're doing this in Excel anyways. I'm going to copy and paste, and now I'm going to change this to 4. Does that make sense what I'm doing? 4 plus 5 plus. So I'm just going to add each of these squared. Does that make sense? Okay. 6 plus, and I'll change this to 7. 7. Okay. And so now I've got the first part of that formula here. What I just did was I did what's in the parentheses here. Okay. Now I've got to subtract the total squared divided by however many samples there are total. Not within an individual treatment, but however many there are total. So I'm going to go minus, this is going to be 17,715 squared divided by, what's the big N in this case? If we have 3 samples each, 5 treatments, exactly, 15. Okay. And I get 1,716,000. Okay, so that's going to be our answer for the sum of squares total. So now we need to get the sum of squares for the treatment effects. So for this one, it's a little simpler. So we're going to take, if you look at the formula here, we're going to notice how we're just working with I here, which means we're just working with the treatments, not the individual samples as well. And if I go back here to jog your memory, it's going to show 60 squared plus 94 squared plus 102 squared plus 127 squared. In this case, it's divided by 6, and those came from 60 squared plus 94 squared. So we're working with 4 here in this example, which is different, and then divided by 6 here. That's how many samples there are. Okay. So what I'm going to do here is just go 2,430 squared divided by, in this case it's 3, plus E4 squared, which is the second one, divided by 3, plus E5 squared divided by 3, plus E, where am I now, 6 squared divided by 3, plus E7 squared divided by 3. Okay, so I've got the first part, and I'm going to subtract, again in this case it's going to be this 17,000 number squared, like we just did in the previous one, divided by 15. And I get 1,645,710. Okay? So we've got the sum of squares so far. Okay? So now we have everything we need to calculate. What are we going to do next? Let's see if we can get the sum of squares error. Remember, there's a total sum of squares, which is summed by the error sum of squares and the treatment sum of squares. So it's simply a calculation, this one minus this one. We solve for the error, and we get 70,350. Okay? What are we going to do next here? We're going to work on the mean square. Let's do the treatment. And recall, on our formula here, we're working with this one. So we just calculated sum of squares for the treatment. It was a 1,645,000. What is alpha minus 1 in this case? 4? Yep, exactly. Okay, so if we go back here, alpha is 4. Why? Because we have 5 treatments. Alpha is 5. 5 minus 1 is 4. Exactly. So for the sum of squares for the treatment, we're going to take the sum of, for the mean squares for the treatment, it's the sum of squares divided by 5 minus 1. All right. Okay, so let's move on and get the mean squares for the error, because we have that formula right here. So this one was pretty straightforward as well. I just took the sum of squares error divided by 10. How did I get 10? It's alpha, which was 5. We just said that. And there are 3 samples each, so 3 minus 1. 5 times 2 is 10. So that makes sense how, notice how both of these numbers look so similar. It's because we divided by 10, okay? So, do we have everything we need now to calculate the F test statistic? Right here. What do you get for the F test statistic? 58? Yes. F. So this is going to be that's what I got as well. So it's the treatment divided by the error. So see how, what we did there is it's tedious, but we just worked through each of these. We're just solving for things, and as long as you can keep the alpha, the A, yeah, that's an A. Not to be confused with alpha, alpha is like the 0.05 usually. We're going to do that here in a little bit. But as long as you can keep the A, which is how many treatments there are, and your N versus your big N and all this stuff, and we're solving for things, the eventual thing we're solving for here is F. You can do it. Okay, so what are we going to do now? We're not done yet. We're almost done. Remember the last step of hypothesis testing? Exactly. We have to accept or reject. So we're going to look up one of these tables, right? You want to go with an alpha of 0.1 or 0.05? Let's do 0.05. Sure. That's pretty common. So we have 0.05, and we have to figure out which of these numbers to use here. Okay. I think I had a slide here that explains it. Okay. So this first one, the numerator, is going to be alpha minus 1. And the denominator is going to be alpha times, I just did it again. A minus 1 is the first one, and A times N minus 1 is the second one. Okay. So what is the first number we're going to look up here? It's going to be this A minus 1, 4, and this is going to be 10, right? Because A times N minus 1. So we're going to go 4 all the way down here to 10. See how I got that? We're looking up what corresponds with this and this. 3.48. Okay. So if we were to draw this on a distribution, and this number was right here, 3.48, and we got a test statistic of 58, which is way over here. Do we accept or reject? We're going to reject the null hypothesis. going to accept the alternative that there's a difference there. Okay? So we just did it. Pat yourself on the back. You can do this. And if you look at these numbers, it's not surprising, right? We go from 810 for a thickness to 1280. As we had different thickeners, we kind of expect something, but now we have 95% confidence that there's a difference, okay? And just for fun, just for giggles, let's see if those values line up with what jump gets. I'm going to stack these columns, and remember how to do the One Way Anova here. I'm going to fit y by x. And where are we going here? Formulation under x. Oop, what did I do wrong? Exactly, perfect. I actually did that on purpose, just see. Because the research shows if you watch your instructor do a mistake, you'll actually remember more. So every mistake I make is planned, right? Okay, here we go. Okay, we get a one-way analysis of data. And if we click on means ANOVA, looky here. This is the one-way and jump. Didn't we get the same numbers here? See how you have sum of squares? Do those numbers look familiar? 171,000, okay. So those are the exact same numbers we just got. And the skeptics always say, who cares about doing the calculation by hand? We have a computer to do that. And my response is, well, we need to keep the computer honest sometimes, you know. And it's nice to look at degrees of freedom, and you can say, is that right? I mean, were there 5 minus 1 degrees of freedom because I had 5 treatments? And you can kind of do the math and appreciate it for what it is. Notice how with the computer it gives you this nice p-value, but notice how like right here, and here we go. Right here, it kind of stopped after this F. There was no P column. But with the computer, it gives you this probability. So we just had a situation like this where our critical value was here, and our test statistic was way over here. So basically what this is saying is 1% or less of the data is here. So there's a very small probability that you're going to be on this side. So in general, we're going to say very small p-value. In a lot of research, people say there's this magic p-value of 0.05. If the p-value is less than 0.05, then we're going to reject the null hypothesis. So the p-value is, in this case, corresponding to the critical value and the F test statistic here. So it's just another way of interpreting the result. In a lot of cases, when you get into research, if you have a computer, it gives you the F, but your eyes are going to go straight to that p-value because it's just a quicker way. The computer basically looked up this F critical value and calculated this probability for you, so you didn't have to look it up. Does that make sense? You could say you're going to reject the null hypothesis because this p-value is less than 0.05. 0.0001, that's a very small probability. You've got a very strong effect there, some sort of treatment effect. Or you could say we're going to reject it because the F test statistic is much greater than the F critical value that I looked up in a table. You can compare each of these means. Thickener 2 is significantly different from thickeners 4 and 3. Did you get that result when you did it? Whereas the control and the first thickener, there was no significant difference between those. So it is pretty handy. If you take a minute to appreciate it for what it is nice to go a step further and say, well, which one's significantly different than the others? Is thickener 4 with the mean of 1,280. Is that a significant difference from 1,205? So at this point, if you think about it, what we're basically doing is we just did a One Way Anova where we compared 5 treatments. Now, in this little connecting letters report, I'm simplifying it very much, and statisticians would say, no, that's not technically right. But basically what we're doing is doing a t-test right here. We're comparing 2 at a time, if you think of it that way. I'm just trying to help make sense of the abstract. So comparing 2 to 4, there is a significant difference there. Comparing 4 to 3, there is not, because they're the same letters. Comparing 3 to 1, there is a significant difference. So you're just doing this pairwise comparison. Technically, it's not right, as the statisticians would say, because if you do a bunch of t-tests, which is a different way, you could just do a bunch of t-tests instead of doing the one-way ANOVA, but you lose power. Yeah, there's a bunch of different comparisons you would have to do. It doesn't give it to you right away. So if you want to talk about why that's technically not the right way to do it, I can follow up with you after class, but it really isn't the point of today. Yeah, Mattia?
So if the p is greater than 0.05, we just simply say we cannot reject it?
There you go. Perfect. Yep. If the p-value is greater than 0.05 or whatever your litmus test is, we're going to fail to reject the null hypothesis, which basically means we're going to accept the null hypothesis. Yeah. Will?
So would the null hypothesis just be that the mean average would be the 810?
Say that, the last part?
Would the null hypothesis be the control?